Say that we are given an array of integers and asked to compute the sum of the values within a certain range of indexes. For example, how might we compute the sum of the entries between indexes 1 and 3? One way to approach this is to simply iterate from the starting index to the ending index. Using this method, we get that the sum is 3 plus 6 plus 4, which is equal to 13. Now, what if we were given multiple ranges and asked to compute the sum for each one? While our approach might still be fine for a small number of ranges, it becomes more and more inefficient as the number of ranges we need to compute increases. To put this more generally, suppose we are given an array of n integers and q queries to process. For each query, we have to sum up the n integers in the worst case, which would take n operations. Since we need to do this for q queries, it would take a maximum of n times q operations to calculate the sums. If n and q are both equal to 1 million, the whole process would take approximately 1 trillion operations, which is certainly too much for the average computer to compute in any reasonable time frame. So, how can we compute these sums more efficiently? The main reason why our method is so inefficient is because we often repeat the same arithmetic operations between each range. For example, in our initial problem, the calculation 1 plus 3 plus 6 is repeated twice. In order to avoid unnecessary repeating operations, we can pre-compute these sums and store them in a separate array. This way, when processing the queries, we can simply reference this array instead of repeating the operations. This method is known as prefix sums. To be more precise, we define the kth term of the prefix sum array as the sum of the first k entries of the original array. Then, for an array of size n, the prefix sum array can be calculated in n operations by cumulatively adding the values of the original array. Now, to calculate the sum of the numbers between indexes a and b, we can simply take the sum from 0 to b and then subtract that by the sum from 0 to a minus 1. In other words, we can take the prefix sum of b and subtract that by the prefix sum of a minus 1. Keep in mind that we do not want to subtract a from our sum. It took n operations to create our prefix sum array, and each query now takes a single operation to process. Thus, our new method takes n plus q operations, which is a substantial improvement from our initial n times q. If n and q are both equal to 1 million, our new method would be faster by a factor of 10 to the power of 6. Now that we've gone over how prefix sums work, let's try applying it to a problem. We'll be going over USACO 2015 December Contest Silver Number 3, breed counting. If you would like to try solving the problem on your own first, make sure to pause the video. Here's what the problem asks. Farmer John has n cows numbered 1 through n lined up in a row. Each cow has a breed ID, 1 for Holsteins, 2 for Guernseys, and 3 for Jerseys. Farmer John wants you to count the number of cows of each breed that lie within certain intervals of the ordering. If we look at a sample input, the number of cows is 6 and the number of queries is 3. Looking at our lineup, the first cow is a Guernsey and the second cow is a Holstein, and so on. The first query asks us to count the cows from 1 to 6, so there are 3 Holsteins, 2 Guernseys, and 1 Jersey. The second asks for cow 3, which is a Holstein, and thus there are no Guernseys and Jerseys. The third query is from 2 to 4, so there are 2 Holsteins, 0 Guernseys, and 1 Jersey. So now that we know what the problem asks, let's go over how to solve it using prefix sums. First, let's just focus on the Holsteins, since once we figure out how to count those, we can just apply the same process to Guernseys and Jerseys. First, we'll make an array that tells us where the Holsteins are. A 0 denotes that the cow is not a Holstein, whereas 1 denotes that the cow is a Holstein. Now, in order to calculate the number of Holsteins within a certain range, we can just add the numbers in that range. Here is where we apply prefix sums. In order to make our calculations more efficient, we will make a prefix sum array of this array. Now for the query 3 to 6, we can just take the number of Holsteins from 1 to 6 and subtract that by the number of Holsteins from 1 to 2 to get our desired answer. We can just apply the exact same process to find the number of Guernseys and Jerseys. That's it! Hopefully you were able to understand how we can apply 1D prefix sums to solve problems like these. Now that we know how to apply prefix sums to one-dimensional arrays, as an extension, let's consider how we might apply the same concept to two-dimensional arrays. Say that we are given the following 2D array and asked to sum the entries over a particular subrectangle. In this case, the sum is fairly easy to compute. However, as before, this method becomes too slow if we are given multiple queries. If we are given q queries to process on a 2D array with m columns and n rows, naively adding each value would cost q times n operations. One way to optimize this is to compute the prefix sums for each subarray. Applying one-dimensional prefix sums to each row, we would be able to reduce the number of operations to n times m for making the prefix sum array, and then n times q for processing the queries. But this can still be too slow. Can we do any better? As it turns out, we can. Instead of creating a bunch of one-dimensional prefix sum arrays to sum entries for each individual row, we can instead create a single 2D prefix sum array. For our 2D prefix sum array, each entry will store the sum of whatever is above and to the left on the original array. In order to calculate the values for a 2D prefix sum array, we'll apply a technique called overcounting. First, we add the prefix sums immediately to the left and immediately above. And now, once we add on the new value, we've covered the region that we wanted to add up. However, since we're overcounting the overlapped region, we have to subtract the prefix sum that is to the upper left. With that, we now have an efficient method of creating our 2D prefix sum array. With this in mind, you might be wondering how this helps us calculate the sum of a subrectangle on the original array. For instance, returning to our earlier example, how might we calculate the sum using a 2D prefix sums array? Once again, we apply overcounting by taking this larger region and subtracting a smaller one. Let's try another. How might we find the sum of this array? This one's slightly more complicated. First, we take this larger region, then we subtract the two regions that we don't need, but since we over-subtracted, we need to add this small region back. Using this method, we can process any query efficiently, now only requiring n times m operations for making the prefix sum array, and then q operations for processing the array. That's it for 2D prefix sums. Hopefully it wasn't too confusing. Don't forget to like, comment, and subscribe. As always, the solution code for the problem is available on our website. Check the description for our website.